So I think in the last lecture, we finished the degree of freedom part, right?
Yes, sir.
Okay. So after degree of freedom, we have to study something called Maxwell's speed distribution. So if you remember the derivation in which there was a large container, and what I said that even if you consider a small part of it, it will contain enough molecules to give you a similar average distribution as you would have got in other part of the volume of container. So if we talk about the individual molecules, the speed is not going to be same. But if you take a collection of molecule over a small volume, then they will exhibit a similar characteristics throughout the volume, which means if I divide this bigger volume into infinite elementary volume, then every elementary volume will have enough number of gaseous molecule to have the similarity with other elementary volume. But if I just take out one of them and try to plot the velocity, on the x-axis, and if I try to plot that a fraction means out of the n number of molecules, how many, so what fraction of molecule having a particular velocity. So this is like a probability distribution graph, because the dn by n is like a probability. So what does it mean is that you would like to plot the probability that out of n molecules, dn will have this particular velocity. So now when we talk about the probability graph in a continuous system, the system at hand is continuous system. Why we are? Because the velocity distribution will have no significant gap, which means every velocity from 0 to infinity is kind of possible. Okay. So the very small velocity is also possible, very high velocity is also possible within the same volume, because the number of molecules is roughly infinite, and therefore it's a continuous probability distribution graph. And if you plot the graph, of the fraction of molecule, so if you plot the graph of fraction of molecule, hello guys, am I audible?
Yes, sir.
Yeah. So n is the total molecule and dn is the a part of n. You would like to plot that what fraction will have what velocity. Okay. Now, what is the probability of molecules with zero velocity? Can you guess? So zero velocity is only feasible at absolute zero temperature, which is 0 Kelvin. But beyond this, as you move away from the absolute zero, to any system that we analyze, experiment with, and possibly we can attain, we cannot attain absolute zero temperature. Although we have gone really close to it, but we haven't achieved the absolute zero temperature. So what is the probability that some of the fraction of molecule will have zero velocity? What do you think? Such probability should be very high or very low?
Very low.
Very low, sir.
In fact, it will be zero, because no molecule can be at rest. Okay. So the graph will begin from origin. Now, a system is defined by a temperature. So if I have a fixed temperature T, And if I would like to express, if I try to keep the temperature, which is the macroscopic variable, to be constant, and for a given temperature, if I would like to plot the graph, some molecule will have, or you can say some fraction will have some velocity in more proportion than other velocity. So if you plot the graph will look like a bell curve, which means the fraction will grow with velocity. But at one particular velocity, the fraction becomes maximum. Let's make it small. It's too big. So at one particular velocity, the fraction becomes maximum. And then after that, the fraction will start again decreasing, because the probability of having very high velocities again. So as v tends to infinity, what do you expect the probability? Can we have infinite velocity for a given temperature? Tell me, guys, is it possible to have infinite velocity? No. So theoretically, such fraction will again diminish to 0. And therefore, you will get a bell-shaped curve around some mean value. You can see that there is one particular velocity which is having maximum fraction. So the fraction is maximum. So this ratio dn by n is max. And this velocity, what we term this velocity as, if you remember?
RMS.
This is called the MP, the most probable. This event is most probable, right? This is called the most probable velocity. I hope you all have studied this in chemistry.
Yes.
So the most probable doesn't mean maximum velocity. The probability of occupying or having this velocity in a system at thermal equilibrium is maximum. That's why the name is most probable. And it is a statistical definition. Of course, this is a something which we have found experimentally, as well as even in practical life also. There is always some value which is always, having the maxima, and the other values will have lesser probability. So VMP represents the event, the velocity which is having maximum takers, or you can say probability, the fraction. So now the fraction, this is the graph is the fraction versus velocity. Okay. So if you add all fraction, what will happen? The sum of fraction is always 1. So the sum of fraction is 1. Therefore, you will always get this. The area under the curve is always constant. It is equals to 1. And therefore, this when you plot a graph, you plot at one particular temperature T. Now, what will happen if I increase the temperature? What will shift? The peak will shift right or left?
Right.
So as you increase the temperature, the most probable velocity will shift towards the bigger value. But in order to keep the fraction constant, the sum of fraction constant, in order to keep the area constant, what do you expect? The peak will have having lower value or higher value. Like should I draw something like this? So you can definitely see that the peak has shifted here, right? And this I have plotted at T dash. The area under both curve will be same or different?
Same.
So to keep the area constant, as it will spread out, it must lower down. The peak must go down, isn't it?
Yes.
So at high temperature, the VMP will shift towards right. And to keep the area constant, it must be lesser in value. And why this is important? Because when you will solve the question of JEE-Mains or advanced, they will ask you graphical question in which you are supposed to guess the correct diagram. Which of the following is correct? So you must know that as T will grow, I must shift the VMP towards right. And as well as the peak must get lower down. It should go below as possible. So as you increase the temperature T double dash, it may go even flatter. Okay, not required. So 2 is enough. You can just compare. So can we say T dash is more than T here?
Yes, sir.
So how to understand which one is having more temperature in the graph? We just check the peak because peak represents the most probable velocity. So a bigger value will be on the right of the origin. So as the velocity, the most probable velocity will grow in value, it means it is happening at higher temperature. So it is representing two separate systems, or you can say it is representing the system at two different temperature. Okay, at thermal equilibrium. Now the question is why this graph? So again, it's a very practical. You can understand through this simple example. Imagine there is a shelf. And imagine there is an infinite supply of balls. Infinite supply. I mean, and we have infinite kids. Okay. So all kids are in queue and they're supposed to throw the ball. So when you give the kid the ball to throw, so depending on the age of the kid, the ball may land on the first shelf or maybe second or maybe third. So imagine if we start with the toddler, then which shelf you think will have the maximum occupancy? The first or the second? Let's say the height of the toddler is more than second. I mean, somewhere here. This is the height. And you're I mean, they are supposed to throw the ball. So which shelf you think will be mostly occupied?
Second.
I think the shelf slightly above the height of the kid will be mostly occupied, isn't it? Because they are throwing it.
Yes.
So you will see that maybe this shelf is having maximum occupancy, but you will find very less number of a ball in this shelf compared to this, and then it will decrease. And maybe because of the practical aspect, you won't get any ball on this shelf. And similarly, the shelf below will have again lesser occupancy because no one is going to throw down. But as the height will grow, the occupancy level will shift somewhere else, right? So now maybe it is possible that this shelf will have more occupancy. And as you go up and down, the occupancy will decrease and so on. So the question is, this is the example, of course, it's a good example to understand. But in terms of physics, what exactly decides that which kind of distribution is the best distribution? Okay. So nature is having some inherent inherent process, and that's called the entropy. So the rule says that the distribution at equilibrium will assume a configuration which can maximize the entropy. Okay. Now you may think, what is the meaning of maximizing the entropy? Imagine if everyone is capable of throwing exactly the same cell. So the ball will be occupied where? At the same shelf, right? So is it a random distribution or is it or ordered distribution? What you will say?
Order.
An ordered distribution means the entropy is less or more.
Less.
If everything is found at one place, it is highly ordered, so the entropy is very small, isn't it?
Very small. Yeah.
But what is the tendency of nature? To maximize the entropy, which means
Entropy.
to maximize the disorderedness, which means
Randomness.
to maximize the randomness, which means to maximize that symmetry So all these things I have discussed in the very beginning of this chapter. The idea is the nature wants complete chaos. Nature wants complete randomness. Nature is unbiased. Nature wants symmetry of distribution. So a symmetric distribution, which I have done so far, is the nature's choice. So the idea is, or you can say mathematically, the distribution will follow a rule called maximum entropy rule. Okay. So it is the property of nature. Nature always try to go from a state to another state naturally, in which the entropy always increases. And when you attain the maximum entropy configuration, the nature will settle down there and no further chaos, no further entropy change will take place. So the nature is having this inherent tendency, okay, to maximize the chaos, the randomness. And so the word entropy comes into picture. So every natural process in nature will tend to move towards a configuration with higher entropy or lower entropy.
Higher entropy.
Higher entropy.
Okay, so you can imagine you're in a school and the last lecture is going on and the bell rings. So just before the bell rings, the order of the school is less or more. Is it disordered or highly ordered?
Ordered.
So the entropy is
Less.
and then all kids will start shouting and running out of their class, holding their bag, jumping, dancing, or doing whatever. So now what is the disorderliness of the school? It is now
Entropy is high.
high, very high entropy. So the nature wants what nature wants, what kid wants. Kid is like nature, okay? They don't follow
Kids
any rule.
wants to get free.
So kids want high entropy, low entropy.
High.
High entropy. Okay. So how many of you want high entropy at home? Okay, none of you. Very good. You all are disciplined now. Anyway, so discipline is against the nature. Oh my God, it's a very secret I have revealed. So discipline is against the nature. Democracy is against the nature. Everything which is ordered is against the nature. And that's the purpose of civilization. Civilization is actually trying to go from high disorderliness to high orderness. And when it is highly ordered, the system is highly unstable. Yeah. So they set them free and then they try to become disordered for some time. And then again, they come back to the same society and become disciplined and ordered. Okay. So what Maxwell said that the distribution of velocity, the distribution is the fraction, having one particular velocity. So there is a function of velocity, and of course you're not supposed to derive or remember, but the FV is a velocity function, velocity distribution function, which we write as 4 pi v square m by 2 pi k b t power 3 by 2 e power minus m v square by 2k. Okay. So this is called the Maxwell formula. Maxwell speed distribution relation, which actually gives you the idea that for a given temperature T, the velocity, the fraction with velocity v will follow this formula. And of course, it is derived. It is not difficult to remember, but yeah, the exponential term is very simple. It's kinetic energy half m square, and kT is also energy. So energy upon energy is dimensionless. So that's good. The term is m by 2 pi kVt, which is like a constant. It comes from the normalization. What is normalization? So I'll come to that. Because this represents a fraction, so we have to understand certain mathematical jargon. Okay, so we are going to understand something called meaning of FVD. So meaning of FVDV. So when we have a distribution graph, when we have a distribution graph, and so what is the probability of having velocity v? What is the probability of having velocity v? So in physics, for continuous function, okay, how many velocity we have here? What are the possible values of velocity? Tell me, guys.
Infinite.
Infinite. So out of infinite, what is the possibility of one of the value?
2 times.
It is 0. See, your sample
Oh,
space is
yeah.
1. Okay, so your sample space is infinity, and your desirable outcome is 1. So what's the answer? It
Yeah.
is 0.
Yeah.
So in a continuous function, the first thing is that the probability of one unique value is always 0. So we never talk about the probability of one particular value. Rather, we talk about a range of values. So let's say if I say V plus dV. Now what I'm asking is, what is the probability that the fraction of molecule will have velocity between V to V plus dV? Now this is the meaning of FVDV. FVDV actually represents, it represents probability that the molecules will have velocity from V to V plus dV. And why it is so? So basically, if this is the graph, okay, this is the graph of, okay, let's remove the D1 actually. Both are same thing, but in a context we have to understand. So the velocity, this is the FV is the velocity distribution graph, and to know the probability that a molecule will have velocity between V to V plus dV, the area under the curve is FVdV, right? Because this height is, what is this height, guys? FV. So what is the area under this curve? So area is length into width. Length into width, isn't it?
Yes.
So every dv represents area under the graph, and we know that the area under the graph always represents the sum of fractions. So this is one particular fraction, isn't it? So we write this way. So dn by n, we always write as FVdV, and this is the formula that you are supposed to understand and remember as well. That the fraction of molecule having velocity between V to V plus dV, we represent by the formula FVdV. Okay. And now why it is important for you to remember, because in JEE-Advanced, they will not give you this function because this is actual function which Maxwell derived. But to make a question, they can create a simple graph, maybe a triangle in shape, and then you need to interpret the graph. So FVdV always represents the fraction. It always represents the area under the graph. And therefore, if you integrate both sides, I'll do it separately. So integration of dn by n is integration of FVdV. And if I take the limit from 0 to infinity, the LHS become how much? Tell me, guys. So LHS is the sum of fraction, which is always
1.
1. So because it is always 1, so we can attest understood. So what you are supposed to remember that FVDV integration is always equal to 1 when you do it for 0 to infinity, means up to wherever the graph exists. Okay. So what kind of question can come? Actually, the function that even Maxwell derived was this. So he got something a 4 pi v square. So he was not aware of the value of a, but he was knowing, okay, that a can be determined by the relation. What relation? That if I integrate from 0 to infinity, I must get 1. So if you integrate this function, so the integration will give you 1, which means the 4 pi a into something is 1. So you will get a from there, isn't it? Sorry. Understood?
Yes, sir.
Okay, anyway. So what you are supposed to remember? You are supposed to remember the meaning of FVDV. FVDV represents the fraction of molecule having velocity from V to V plus dV. And we write dN by N as FVDV. So what is FV going to be? We do not know. It depends on the question. So it is the examination. In examination, they will decide what FV they want to put. So they will give you some simplistic FV value, which you can easily find the area. It may be some sort of rectangle, I mean, maybe triangle or whatever. So what are the applications? So because you know the function FV, and it is 4 pi V square into M by 2 pi. K is Boltzmann constant. Okay, so this is the formula. Now tell me, guys, if a function is given to you, can you find the maximum? For what value of V, the F is maximum? So for FV max, the D of FV by dV must be 0 because we are doing it at one particular temperature. So your temperature is constant. Okay. So if T is constant, then for what value of velocity the function will attain the maximum? Because you can see in the graph we have a peak, right? This is the peak. So we would like to know what is the V at which this is maximum. Because when you get this answer, what you get is nothing but the. So this is the way to derive the most probable velocity. Understood? So how to derive the most probable velocity? By differentiating the function and making equals to 0. Is this clear? So can you guys differentiate this?
Yeah.
Because see, M by 2 pi kt is a constant, 4 pi is constant, so you can ignore that term. So you're actually supposed to differentiate d by dv of v square and I think this is not difficult for you to differentiate. Use the product rule and differentiate and equal to 0. So once you differentiate, just let me know what you are getting. I think you are not interested. So v square into I think this is correct.
Yeah.
Yes.
So we are going to get here V square into M by KT equals to 2, right? So V square is how much? 2 KT by M. And I hope you know this answer, that this is the most probable velocity formula, right?
Yes, sir.
Yes, sir.
So most probable velocity formula is actually the maximum probability. It is not the maximum velocity. And the name itself is the explanation, that most probable, which velocity will have the maximum take us, maximum fraction of the system will have this velocity, which is 2 kbt by small m. If you want to write in terms of molar mass, you can write as 2 RT by capital M, right? So this is what you should know, that how to do this. Now the function can be given to you, will be easier one. You may be given some graph as well, and you're supposed to interpret it correctly. So now the question is how to explain the average velocity. What is the average? So in a system of molecule, let's say dn molecule having velocity v. So how you find the average? dn into v. Then you add all values and you divide by dn, right? This is how, what you do for the discrete values, isn't it?
Yes, sir.
So when it comes to the continuous value, the summation will be replaced by
Integral.
integration. So what we write is v dn, it looks nice, upon dn. So this is how you have to use the average formula. So what is the thing which you must understand here is how to write the average formula. Again, the dn by n will be given to you. And we know that since dn by n, we can always write as fv dv. So dn we can always replace by which relation? N times fv dv. Understood? So now this equation and this way of writing will help you in getting the relation. So you can write v into n fv dv upon n fv dv. And because n is constant, so we can take it out. So what we're left with is now v, the function given to you, dv upon fv dv. And then you have to integrate from 0 to infinity, because that's the range of velocity in our case. Now, if you exactly use the function given by the Maxwell, you will get the formula which you know very much. So you have to do the integration by parts in the numerator and in the denominator as well. So that will be cumbersome for you. But if someone can do at home, you can practice this. The answer what we'll get is 8 kt by pi m. That's the average velocity, isn't it? I hope you have studied this chemistry.
Yes, sir.
So either you can write this way, or you can write as 8 RT by pi capital M if you want to write in molar mass. So these are the actual derivation of average and the most probable. In fact, Maxwell distribution is why it is famous, because see, the RMS value we have derived in a different way as well, using the Newton's laws of motion, right? But luckily we can derive that also using the Maxwell distribution graphs. Okay. So what is the definition of RMS? Root mean square. So first you square the function. So V RMS definition is square the function, isn't it?
Yeah.
Hello. So V square dn. Take the average, so divided by dn. Take the root. So this is the way of writing the RMS. Now in examination, they will ask you which of the following way of writing is representing RMS. At least you should know, okay, this is the way of writing. Is this clear, guys? What I have written here?
Yes, sir.
And
Yes.
once you do this, of course, if you do the integration, which I doubt, but anyway, if you do at home, you'll get the answer as 3 kT by m or 3 RT by capital. So all the types of velocity which we define statistically or you can say mathematically can be derived by the single Maxwell distribution. What we can expect in JEE? So in JEE means they will ask you the meaning, the interpretation, like how to write the RMS. So you have to understand it's a V square dn by dn. How to write the average? It is V dn by dn. How to write the VMP? So differentiate the function and equate to 0. So these three things you're supposed to remember. Okay. I hope this is clear to all of you.
Yes, sir.
Yes,
The
sir.
Maxwell distribution part. So after the Maxwell distribution, what else we need to know? Okay. So they will give you some graph, okay, and they will ask you the temperature relation. They will ask you the VMP relation and so on. And if you remember only these three things, it is more than sufficient. So from Maxwell, this is what you are going to get. Now we have to understand two things. Mean free path. Symbol is lambda. So what is mean free path? It is the average of separation between two successive collisions. Okay. So on an average, how much a molecule travels before it hits the next molecule? That's called the free path. And then if you take the average of all such paths, it is called mean free path. So mean means average actually. So definition is, okay, we have done this many times before. Let's do it once again. So what is mean free path? It is the average of distance that a molecule travels between two successive molecules. So the path of a molecule, if this is a molecule, it will definitely travel randomly so between so you travel this much lambda 1, then you travel this much. After deflecting, you travel and then you collide here again. Then again you travel and collide. You travel and collide. Travel and collide. And so this will keep continually, happening here. So the average of all such values is called the mean free path. It is actually lambda 1 plus lambda 2 dot 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 whatever lambda n. So this is called the statistical parameter. So it's not observed actually, rather it is predicted. Okay, so we always try to rely on the probability, and the probability will work fine because once you have this probability understanding, and if you try to predict something, if it is matching the outcome theoretically and experimentally, it means our model is correct. So that's why these are called theoretical, statistical parameter. So this is statistical parameter. So we have discussed all this in past days, right? So how to derive the mean free path? Now we'll try to understand the mean free path through the shape of object. So here the object is molecule, and imagine it is moving or traveling in this particular direction. So you can clearly see that the path that this molecule will occupy is this path, right? So what is the condition for collision with this molecule? Who all will collide with this guy? So the answer is very simple. Anyone which is in path of either here. Let's say if you're here, you're definitely going to collide. Here, collision. Here, collision. Yes or no? Tell me.
Yes, sir.
Yes, sir.
So for collision, what are the possibility? the center bit, the separation between the center should be less than how much? 2R, isn't it? You can see clearly.
Yes.
Even if you are here, you're hitting it, right? So the separation between the center of the first and the second molecule is less than 2R. Yes or no? Tell me.
Yes, sir.
Yes.
So in the worst case scenario, I can take almost 2R for calculation purpose. Yes or no? Tell me.
Yes, sir.
And the same thing will happen here also. Yes or no? Tell me. So basically, if I draw one molecule here and one, and if I draw one molecule here, and then if I draw a path something like this, just a moment. So this is our cylinder. This is our cylinder. So can we say that every molecule within this cylinder will have the chance of hitting it? Can we say?
Yes.
So this is called the effective volume. And this effective volume is equals to the diameter of the molecule, isn't it? I mean, sorry, the radius of the cylinder is equals to the diameter of the molecule. Yes or no?
Yes, sir.
So because this is the diameter of molecule, I'm assuming all molecules to be identical. So D is called the diameter of molecule. So if the velocity of this molecule, if I assume the average velocity to be V, let's say this is the V is the average. In time dt, how much it will travel?
VDT.
VDT. So let's say okay, I'm assuming the length of cylinder as VDT. Highly exaggerated one, but this is the length. Let's call this is VDT. So let's say in time dt you travel this much. And what we can, I mean, assume here is N. What is N? N is called the molecular concentration, which means number of molecules per unit volume. Okay. So now tell me, how many molecule you can probably interact with in this motion, assuming that you are only moving, everything else is frozen, like a statue. So everyone is static and only I am moving. So what are the count of molecules I am going to probably hit? So the
VDT.
volume, yeah. So the volume swept is how much? The volume swept is pi d square VDT.
Yeah.
Yes.
So can we write the volume swept in time dt equals to pi d square into VDT? Tell me guys, is this clear what I have written here?
Yes, sir.
If this is the volume swept, then how many molecules I can meet in my journey?
Pi d square VDT by N.
By N or into N?
Times
Sir, by
By N is the number of molecules per unit volume, and you have traveled this much volume. So how many molecules you will meet? How many molecules are present in this volume? Tell me.
N part.
Sir, N into the volume.
yes, that
Yeah.
will be N into.
So that many molecules you are going to meet, yes or no?
Yes, sir.
Yes, sir.
Therefore, the number of collision is how much? Number of collision, or you can say collisions, equals to how much? The number of collisions is how much?
Sir, n into volume.
Right? So if this is the number of collisions, I don't know what is the symbol. So what is the number of collisions per unit time?
Divided by dt, sir.
Yeah. So number of collision per unit time is n pi d square v, right?
Yeah.
This is called collision frequency, like how many collision per unit time you make. Now you're not supposed to take this as correct answer, but the collision frequency will have the order. They will generally ask you the order of collision frequency. So you can say collision frequency is of the order of n, or you cannot like this, pi n d square v. Anyway, but this is not our concern. What we are trying to find here, mean free path, like how much you travel without hitting anyone, right? Or what is the average separation between two successive collisions? So how we are going to get this answer? Any guess? Tell me how much you travel in reality. The molecule has traveled how much? The molecule has traveled only VDT, no?
Yeah.
Yeah.
But while traveling VDT, how many person you met? Tell me. So how many molecules you have met in your journey? So you have met n into
The
pi
volume.
d square.
Volume. We did.
See, you met these many guys while you walk only VGT. So what is the average, separation between these molecules on an average? The answer is how much? 1 by pi d square n. Or you can say n into pi d square, where d is the diameter of the molecule, n is the concentration molecule. But this answer is not correct. It is called empirical relation. This is the empirical relation. But because of the randomness, see, I assume that everyone is static and only I am moving. But is this the reality?
No.
See, everyone is moving, isn't it? So, to solve this question, we are supposed to do some more mathematical calculation, which is not required for you. But what you need to remember is that the randomness will add more collision than what we have calculated, isn't it? Can we say the
Yeah.
randomness will have more collision than what we have calculated? So the
Yes.
actual collision is found to be root 2 times what we have calculated. So you can think that the actual relation we assume as, so we have to multiply with the root 2 terms because we have more number of collisions than what we believed, and therefore the formula becomes root 2 times pi d square n, and see the formula for the mean free path. How we derive this formula? I mean, there is a simple way of derivation. So if we consider two molecules, what is the relative velocity of the two? You can say v1 minus v2, isn't it? And if you do so, what is the average? I mean, what is the modulus of these two? So v1 square plus v2 square minus 2 v1 v2 cos theta. Am I right?
Yes.
So if I square both sides, the relative value, I will get V1 square plus V2 square. Okay. So what I'll do is I'll take the average. So if we take the average of each term separately, let's write it down like this. So because of the randomness, the cos theta will always give you zero answer on an average, isn't it?
Yes.
Because if you integrate from 0 to 2 pi, I mean, in two-dimensional view, it is always 0. So this term always gives you 0. So what you are getting is only the first two terms. And because we know that every term is equal on an average, so this is also V square, this is also V square. So the average of a relative is basically 2V square, right? So what is the average of relative? So the average of relative turns out to be √2 times V. And that is why in the volume swept formula, we have to use the √2V as a relation, not as a V. And that's why the formula will have the √2 in the actual answer. So this is how we derive it, but we modify to this value, and this is the derivation. None of this is required to you. Just remember the formula. In case if you forgot, you should know the derivation. So the distance traveled upon number of collision, distance traveled upon number of collision, distance traveled upon number of collision, and therefore the concentration will come into picture for sure. So the mean free path we got is 1 by √2 times pi d square n. Now there are many ways in which we can express this answer, and for that we have to go back to the first lecture in which I have shown you how to write the ideal gas equation in different format, right? So just to recap, PV equals to, what is this n representing here?
Number of moles.
It is number of moles. So this n is not the n here, right? So this should
Yeah.
not confuse you, right? Okay. We can also write as PM equals to rho RT,
Yes.
and we can also write because mole is defined as molecules upon Avogadro number in terms of number value, isn't it?
Yeah.
So we can write as N by V R by NA into T. What is N by V, guys? This is called the molecular concentration, means C, and R by N is called the Boltzmann constant, K and T. So we have P equals to CKT. So C we can replace by, and that is why you should know this. The lambda can also be expressed as the n we can replace by P by KT. So lambda is proportional to, you can say, in terms of thermodynamic variable, T by P. Now, if someone will ask you that lambda depends on temperature, is this correct or false? Lambda depends on temperature.
Correct.
Lambda is inversely proportional to pressure. True or false?
Yes, sir.
Lambda is directly proportional to temperature. True or false?
True.
So all these answers are incorrect. Always remember, because the derivation that we actually did was this. And to answer any theoretical question, we have to understand only this part. And the concentration is amount of molecule which you have actually put in the vessel. And diameter is God gifted. √2 is constant, n is constant. So none of this quantity depends on temperature or pressure. Understood?
Yes.
See, if the space of the vessel is constant, if the volume is constant, if the molecules are fixed, then lambda cannot be changed. Is this clear to all of you?
Yes.
It is like how many person is in your room. So just because if you switch on the AC, the lambda will decrease in your home. Or if you switch on the heater, what will happen? The lambda will change. Your room size is fixed. The number of people living there is fixed. So the mean free path is constant, isn't it?
Yes.
Mean free path depends on what is the number of person living in that volume. That's it. If that is not changing, how you can change the lambda? Understood what I'm saying? Definitely the temperature change will affect the what? Temperature change will affect
Time of relaxation.
exactly.
Okay, sir.
Because as you increase the temperature, the frequency with which you collide will be less because you are moving faster, so you will hit more frequently. But other than that, can we change the mean free path? So just because we are able to express in terms of temperature and pressure, does it mean it depends? That's the big question. Tell me guys, is this clear?
Yes, sir.
So don't get carried away by the formula. Okay. The formula to answer theoretical question is this only. So use this to answer theoretical question. I hope this is clear.
Yes.
Okay. All right. The next part. So now, once you get the lambda, the next derivation which you must know is mean time of relaxation, which is again very easy. Mean time of relaxation which we represent with the tau. So the mean time of relaxation is that how much you relaxed between the successive collision, right? So we know that this is very simple. How much time you spend in that cylinder? D2. And in time dt, how many collision you made? Now can I write root 2 VGT into pi d square n? I'm making this calculation here itself. Earlier, I used to write VDT, right? The distance upon number of collision. What I'm writing now? Time upon number of molecules in that volume, isn't it?
Yes.
And I'm putting the root 2 because that was the change, or that was the modification which we did using the randomness concept. So because of the randomness, you will of course make more collision than the empirically derived relation. So how many of you are able to get this relation? This is simple.
Yeah.
Time traveled molecules collided in that duration. And therefore, the tau will have the relation 1 by root 2 times pi d square n into V. And if you remember, this was actually by definition lambda, right? So the average time of relaxation is actually lambda by V average. So we always write like this. So no need to remember this derivation. If you just remember the lambda and if you divide by the velocity, you will get the mean time of relaxation. Is this clear?
Yes.
So because lambda, okay, what you are supposed to remember, let me tell you what you should know. Lambda is proportional to, tau is proportional to lambda. Lambda we got is T by P, T by P. And then V we know is proportional to under root of T, if you remember. So V average is how much? 8 RT by capital M. So anyway, any velocity is always proportional to root of T. That's very logical. Because KT represents energy, right? So the T under root T will represent the velocity. And because of this relation, when you're solving the question, the tau average should take as proportional to root T by P. So now let me write down all the formula at once. Lambda is, I mean, why I'm writing tau average? This is itself is average. So this is extra redundant term I'm adding here. Anyway. So lambda is T by P. And you just need the proportional relation to solve numericals based on lambda and tau. Is this clear?
Yes.
Okay. So if you know this much, this is more than sufficient from the point of view of lambda and tau. So just remember. And what is collision frequency? So collision frequency is inverse of tau. Okay. So you may write frequency equals to 1 by tau, and this will be definitely 1 by tau is how much? V average by lambda. And because it is inverse of tau, so we can write as P by. So collision frequency is going to be proportional to that's it. So I hope this three formula is sufficient. Just remember this. This is the most important formula for you. Is this clear, guys? Tell me.
Yes.
Yes, sir.
So now we can do few, I mean, a small derivation. And why derivation? You're not supposed to remember the derivation. I mean, for mains part, of course, for advanced, you need to know exactly. But for answering the graphical question, you should know. So we are going to do some standard derivation, which you can see directly asked in the examination. So this is called the variation of pressure with height okay under isothermal condition. So technically, if you go above the Earth's surface, the temperature will fall down. So when you're flying within a plane, then the temperature generally outside is minus 40 degrees Celsius. Isn't it? Hello, hello, hello.
Yes.
Yes.
So the height of the plane is roughly, I think, 30,000 to 40,000 foot, right? So that is the
Yes,
height of the
sir.
plane in that case.
Yes, sir.
But if you go to the Burj Khalifa, from the base to the Burj Khalifa, the temperature will change by less than 1 or 2 degrees, right? Not much.
Yes, sir.
So for a small height, I mean, we can assume the temperature to be almost constant. And under this assumption, we are going to derive the relation. So here you need to know certain more things, that how temperature, how pressure varies under the condition and in atmosphere. So these are, we are doing variation of pressure with height actually for atmosphere. The variation of atmospheric pressure. And again, I'm saying this is very standard. I mean, it is in every book of graduation level book, if you study, which are not supposed to, but you should know this. So under this isothermal condition, how pressure will vary? So imagine this is the Earth. And the way to derive is very much typical. Just to try to understand once, and hopefully you can derive all other relation in future as well. So let me draw the atmosphere. And this kind of derivation is also typical of the derivation in the fluid mechanics. Okay, now I'm getting tired, so I'm just draw like this. Oh, this is nice atmosphere. Fine. Mhm. So at sea level, I'm going to assume the pressure to be P naught. Oh. And now I'm interested in finding the pressure when I'm at a height edge. So you can move vertically above the Earth's surface. And you can draw a. So how we deal with this atmospheric thing? So as you go up, if the pressure will decrease, then the density should also decrease, isn't it? So imagine a thin cylinder. Of air. So I have assumed the air of, okay, the vertical height dh and the height from the base as h. So after h, I cut a small cylinder of height dh, and I'm going to consider the area as dA. It's a very small. And this system, I mean, this air trapped in this cylinder, that air is at equilibrium, yes or no? Is that cylinder going up or down? Or is that air at that same location all the time, ignoring the turbulence? So can we say the entire air is kind of at static equilibrium? Yes or no? Hello. Tell me, guys.
Yes.
The entire air is at static equilibrium
Sir, how is it static?
because it is not moving. It is at rest with us to the earth.
Sir, the composition is always constant.
Static means if you take the entire cylinder as a one system, you're not supposed to see with what is happening within. So if I draw some arbitrary layer, okay, imaginary layer, then what you will see is the entire cylinder at once, right? And then you are supposed to think that is that cylinder moving or at rest? So
Oh.
let's say you have a jar of honeybees and you close the jar. So of course within the jar the honeybees will be making the random motion.
Yes, sir.
But the jar as a whole is at rest.
Yes, sir.
So we call that jar as at static equilibrium. Understood?
Yes, sir.
So when we talk about the system, then we talk about the center mass, not the individual molecules. So the center mass of the system is at rest. So that's why the system is at static equilibrium. I hope this is clear.
Yes, sir.
Yes, sir.
Now you can always draw, see, whenever you're solving the question of either liquid or gas, we know how to solve question of laws of motion if it is wedge, block, plank, and so on. But we find it's really difficult when you solve question of gas or liquid. And the reason is we do not see a finiteness. And therefore, to solve any question of fluid mechanics or gaseous state, you can always cut a small piece of it arbitrarily and think as a block or cylinder or plank or wedge, whatever you want to use. That way will give you again access to the laws of motion, which you can apply and you can solve. So if I draw this, now I'm going to draw the ABD, free body diagram. Because DH is really small, can I assume the density of the gas at this location as rho?
Yeah.
So what is the mass of this system?
Rho DHDA.
Very good. So this is the mass. So gravity will pull downward, just like laws of motion. See, I'm not doing anything extra. If you
DMG.
understand the laws of motion, you can always write DMG, right? So technically, if DMG is the only force, it must descend, it must go down, but it is at rest at that location, which means some other force must be acting, and because it's a gas, it's a fluid, so it will exert the pressure. How the pressure will act? Now there's a way to assume also. So pressure always acts normal to the surface. So at the bottom surface, it will act upward, but at the top surface, it will act downward. It is clear so far?
Yes.
And then
Yes.
the force due to pressure, there is a way of writing. So we always assume the pressure at height h as P and at height h plus dh as P plus dP. This is how we assume pressure mathematically. So when you have the incremental change in the height, the pressure will also change. Okay, element.
But it will drop.
Yeah,
As you
that's
go
not your
upward.
concern because the dP can be negative, isn't it? So plus doesn't mean we are increasing. In calculus, we always write something plus. So if a function is x and the value is y, if it is x plus dx, we write y plus dy. The dy could be negative, isn't it? So adding dP doesn't mean it's making it bigger. Is this clear what I'm saying? So mathematically, we have to add the force. What is the force? PD. And what is the force here? So any other force you can see here? No. So now you can add the equilibrium condition. So for equilibrium, what we have to write? Tell me, guys. Rather, you all should write actually. Because once you write, you will realize something. So please write the net force equals to 0 and tell me what you are getting after writing net force equals to 0.
dP by dH equals minus rho G.
Yeah, you first write and let me know. So what you're getting? dP by
dP by dH is equals minus rho G.
are you guys getting all are getting the same answer?
Yeah.
So dP
Yes.
by dH is minus rho G. So it means the dP we can write as minus rho G dH. So you want a variation of pressure. So density is also going to vary, but we do not want density. So we must eliminate this. So this will be your first question. The second will come from the actual gas. So ideal gas equation of that location, what we can write, if you remember? If at this location pressure is P, density is rho, the molar mass of the molecule is M, temperature is constant, it's called T. So what is the relationship between pressure, density, mass, T, if you remember?
PM is equals to rho
by
RT.
RT.
So it is rho RT by M. So PM equals to rho RT.
Yes, sir.
What you don't want? What you want to replace here?
Density.
So divide these two equations, that's easy. So 1 divided by 2, what will get? dP by P equals to, or PM, minus G dH by T, RT actually. correct? So dP by P is how much? Can you integrate? I am also taking G as constant. So when it is 0, what is the pressure? And I hope you can understand this. This is the exponential relation. P equals to P naught E power minus mgh by RT. So it will decay exponentially under the assumption that the temperature is constant. So the graph is very simple. So it will start with P naught, but as you go higher, it will decay exponentially. I hope you all can understand this.
Yes, sir.
Yes, sir.
Yes.
So in examination, what they will ask you, none of the derivation, they'll ask you which of the following graph is correct representation of pressure versus height. Under the assumption, it is varying isothermally and G is also constant. So you need to understand the two-step process. One step is of course from the gas equation, and other is from the equilibrium. So whenever you're solving question of either gas or liquid, you always have to do this two-step process and you will get the answer. Now, once you get the pressure, you can also add the variation of density because pressure will vary, so the density will vary, and so the concentration will vary. So if I assume that density at the bottom as rho naught, if I assume the concentration as N naught, all three will vary in the same fashion. Why? Because P and density are proportional. So dP by P is same as d rho by rho.
Yes.
I hope you're not taking this. From the ideal gas equation. Oh no. Again, you have to always recall this relation P equals to Pm equals to rho RT. If I assume the temperature to be constant, then the P is proportional to rho. Tell me, guys, can we write like this? And therefore, the dP by P will be equals to d rho by rho. If something is proportional, then the fractional, the ratio must be same.
Yes, sir.
And we also know P equals to CKT, where C is the concentration, which I have taken N naught. So P is again proportional to C. So dP by P is also dC by C. Therefore, all three relations in this particular case will have a similar graph. So you can write a rho equals to rho naught E power minus mgh by RT. And we can write concentration equals to C naught E power minus mgh by RT. And of course, we have the pressure equals to E naught E power minus mgh by RT. So all will follow the same relation. And therefore, sometimes they do ask the question that what is the center mass of atmosphere? Find the center of mass of atmosphere from Earth's surface. So from the sea level till the zenith, draw a infinitely long cylinder. Like draw a cylinder which is varying from where to where? From ground to infinity. So that cylinder will contain all the gas from bottom to the top, isn't it?
Yes, sir.
In that case, we know that YCM we have to find equals to, the formula is what? Y dm by dm. And the mass you can add as density into volume. But density here is variable. So I cannot take outside. And volume you can write as cross-sectional area into height. So this will become y rho dy, because I'm replacing h by dh by dy. And area term will cancel out, right? I hope you can understand this part. Rho I think you're not doing this one. So because this is the infinite center, right?
Yeah.
From the base of Earth to the infinity. And this is your elementary mass. If I assume the cross-sectional area is A, this is dy, this is y, and the density of this location is y. So what is the mass of this part? dm equals to rho a dy,
Yeah.
and that's why the a will get cancelled from the numerator and the denominator, because a is same right throughout the assumption. This is the Earth surface. And then you have to integrate from 0 to infinity, because technically our answer is up to infinity. And the y is y. The rho we know is rho naught e power minus mgh upon rt. Rho naught so you can also find the height of center mass of Earth's atmosphere. So anyone who can do this integration, rho naught will cancel out. So it will turn out to be, I think, RT by mg. Hopefully, that is answer. Okay, so don't do this. I mean, you can do at home. So the answer will be y sim. You will get answer as RT by mg. Also, you can think dimensionally, y is the height. So RT by mg will have same dimension as height. So just look at the formula here, and you know the answer. Okay. Is this clear, guys? Tell me.
Yes, sir.
So this is the height of atmosphere. Okay. The next part is there are two major derivation. Should we do this? Okay, anyway. A variation of temperature with height under adiabatic condition. Okay, I think if you don't know adiabatic, then I will skip, but I hope you know from the chemistry. So adiabatic condition means as we go up, temperature will vary, yes or no?
Yes.
So in adiabatic,
Yes.
everything varies: pressure, volume, pressure, temperature, of course, density, everything will vary. Nothing is constant. What is constant is like there is no heat exchange between the system and surrounding. So that's why it's called the adiabatic condition. The energy of the system remains, I mean, not constant, but the energy of the system, I mean, it will never absorb the heat nor release the heat. So the heat transfer is 0. So of course I will teach you in the first law, but should we do this later? Or you want it right now? Or you want after first law? Tell me guys, you want right now or after the first law?
Sir, I think right now is fine.
Yes.
Okay. So we know the relation PV power gamma equals to constant from the adiabatic process. We
Yeah.
also know TV power gamma minus 1 equals to constant. Okay. Now, first of all, I will tell you how to differentiate. Because every time you're solving question of thermodynamics, you need to use the either ideal gas equation or the guiding equation. These are called guiding equation of the process. This is called guiding equation for the process. So every thermodynamic process will have some guidance or guidelines or guiding equation that you must follow. And these relations are called the guiding equation. Okay, they follow it actually. And the ideal gas equation is always there. And the ideal gas equation will help you in converting the or changing the variable. So see, the first relation is P and V, or the second is T and V. And because I want the temperature and the height variation, so I will go with T and V because V volume will have height inherently, right? So you can again think as a infinite cylinder and proceed accordingly. First of all, you have to differentiate to get an elementary or differential equation. So this we can differentiate. And the way of writing is dt by t, the partial, you can say derivative, not partial derivative. This is the fractional value of t plus the power gets multiplied and dv value. This is 0. So every mathematical relation in which we have only either product or division or power, the way to differentiate is don't differentiate, rather write the fraction, and if you see some power, multiply with the power. If you want to understand why it is coming this way, so you can take log both sides and differentiate. So that is not required. Okay. So we have done this in the error analysis, right? How to write fraction. In
Yes.
error, the only difference is there we always used to write the positive value, but here, if the things are in denominator, you have to make it minus. Okay, which means if I have something a by b, and if I'm solving question of error analysis, I'll add dz by z, dA by A plus dB by B. This is the error analysis. But in general, what you write? dz by z, dA by A minus dB by B.
Yes.
So you have to be careful that error we always add things, but in general, when we differentiate something, depending on the power, we have to multiply or divide. I mean, we have to add or subtract both. I hope this is clear. No.
Yes.
Yes, sir.
So now once you get dt by dt, I mean this dv by v, we know that dv by v we can write. We know how to write dv by v. So how to write dv by v? So this is the one equation which we need to know, and one equation which I always use. So from previous derivation, the laws of motion will remain same everywhere, isn't it? Which means dp will be always minus rho g dh. Hello, isn't it?
Yes.
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 dp is always minus rho g dh. This is always, I mean, you cannot get beyond this. Okay. And now this gives me one more idea. Because here I am getting dp and I need temperature and height relation. So I have to also replace dp. The question is how we are going to replace dp. Any idea? So you can always use the the relationship between the temperature and pressure directly, right? I hope you remember this. From the adiabatic process, we have three relations: temperature, pressure, temperature, volume, pressure, volume, right? PVT. So we have three C2 relation. These two, or these two.
Yes.
So if you write the temperature and pressure relation, you will get the third equation, because see, I do not want pressure, so I have to think about how to replace it. And the only thing I have is the guiding equation, because the process is given, so the guiding equation is given. All right, all right. So how to proceed, guys? Tell me. You have to do one more step here. So let me write down that step first, then I'll write this again. So P versus T relation, how to replace? So volume is PV equals to nRT, so V equals to? So V is proportional to T by P, isn't it? So you can write V as T by
Yes,
P
sir.
power gamma minus 1. Once you know the proportional, you can always replace. So what you get here? P power gamma upon P power. And now you know how to differentiate this. I have explained you. So to differentiate, we can write gamma dt by T equals to gamma minus 1 dP by P. It is clear, guys?
Yes, sir.
Yes.
So dP by P, okay, I can replace from here. So you can write dt by T is gamma minus 1 by gamma. And dP, how much we got? Okay, I have to write that equation. Okay, first of all, this. And then from laws of motion, from equilibrium of gas under gravity, the dP was minus rho g dH, right?
Yeah.
Yeah, we can replace this dP here. So okay, this is not required. I can remove this part. So dt by T equals to gamma minus 1 by gamma into dP is minus rho g dH by P. Still, it is not sufficient, because again, rho and P both cannot go together. I need only H. But now comes the ideal gas question for your rescue. Now, Pm equals to rho RT. So rho by P is basically how much? M by RT. Now that is what will help you. So dt by T is how much? Gamma minus 1 by gamma minus GDH. And what is rho by P? M by RT. And this T gets cancelled. Now this is really nice. So dt is how much, guys? Minus mg gamma minus 1 by gamma into dH, right? And now it is totally integrable, because everything else is constant. So when height is 0, let's call temperature as T naught. So when height is S, temperature is T. So T minus T naught is how much, guys? Minus mg. Yeah. You know what is alpha here? Mg gamma minus 1 by gamma. This is called alpha. Alpha is called adiabatic lapse rate. Adiabatic lapse rate. And this is responsible for the precipitation, which means as the steam, when vaporization happens at the sea level, as it rises up, the temperature starts falling. And then at one particular temperature, it starts condensing into snow. Understood? And that is how precipitation process will create the clouds. And why the clouds are floating? Because it is still having, packing of air. Now you may be wondering that why cloud is not falling down because of gravity. The answer is simple. The condensation process will, of course, condense, but the overall density of the cloud will be less than the dry air. Because water as a molecule, if you remember the formula is H2O. What is the molar mass of H2O?
18 units.
18.
18. But if you think about the molar mass of nitrogen, it is
14.
N2 is how much? N2 is
14.
14. N2 is molecule. No? What is the molar mass of
28.
28.
28.
And
Sorry.
for oxygen?
16.
32.
32.
32.
So if these masses are much heavier than water molecules, it means that dry air is actually heavy. It remains below and the clouds are actually lighter. Okay, so it goes up. Now what happens as the precipitation will continue for a long time, it will reach the saturation, the saturation vapor pressure. It means you cannot further condense. When that limit is reached, then the precipitation or what we call the raining starts. Okay. So in nature, as we move up, the temperature will decrease, and therefore they will ask you graph. So under the adiabatic condition, the temperature and the height will be a linear graph. Okay. Something like this. And the alpha is basically the adiabatic lapse rate, because if you write dt by dh from here, from this equation itself, you can say dt by dh is how much? Minus dt by dh is, you can see the answer, mg gamma minus 1 by, I have missed something, r was there, no? Yeah, I missed r everywhere. Yeah, that's right. So this is the rate at which the temperature will fall, and under the under the adiabatic condition, you can see this is constant, right? Mg is constant, gamma is constant, r is constant. So this is entirely constant, and this constant we call alpha, and so we call the adiabatic lapse rate. So this question is very, again, a typical question. Everywhere it is there in Erodov or in any graduate book, or in Olympiad also they have asked this question as a comprehension. Okay. So this was the, of course, a difficult derivation, but you should remember that the graph is straight line for temperature, and for pressure it is exponential decay. Is this clear, guys? So
Yes,
in fact,
Yes.
in fact,
Yes.
as you go up, the temperature will fall for I think every 165 meter, temperature goes down by 1 degree Celsius. I think this is what we studied. I studied in high school in geography, maybe. Okay. So this is the end of the KTG part. Now we're going to enter the first law of thermodynamics. So in the thermodynamics, we have to first understand the concept of work done by the gas. Work done by the gas. So because you are preparing for IIT-JEE, so your aim is to become an engineer, right? Of course, later on you can become the stand-up comedian, but that's a different story. So work done by the gas. Why we want gas to do the work? Because we are writing work done by the gas. Because as an engineer, do you want to work or do you want to design a system that can work for you? Tell me.
Second option.
Design.
You always want to design a system that can work for you. So it's very interesting. I mean, story. So when you rub your palm, you see that it produces heat, right?
Yes.
So it is very natural that a mechanical work can be converted into heat. So any frictional work is naturally creating the heat. So it is known to the mankind since very long time that it is easy to convert the work into heat. So after a long time, people will start thinking, okay, can we do the reverse process? Like, can we make work using heat? Okay. And that establishes the concept of heat engine. So basically we say engine is a device which can convert heat into mechanical work done. So we are trying to create some sort of movement, and what we are using is the heat. But to create the movement, we need some expandable object. So if you heat a metal rod directly, will it move significantly? If you heat directly the piston, will it move significantly? The answer is no. So we need something which can expand drastically. And what could be better than a gas? So the gas having the property that when you heat, it can expand. So if you kind of confine the gas within enclosure, and if you attach some, sliding objects or like a piston in a cylinder, then the expansion of gas will naturally move the piston. And once the piston has moved, the work is derived. And once work is derived, you can do it for the running of motor vehicles, bike, train, plane, or whatever. So that is how the idea came into picture that can we do this? Okay. Can we design a system which can work for us? In turn, okay, my job is to give the energy. So what I will do is I'll give energy, and then through the idea of expansion of gas, I'll create a system, and that will do the work. So in our case, when I say the word engine, engine always refers to piston cylinder arrangement. There's nothing like engine. So it's simply any piston cylinder arrangement is your thermodynamic engine. It is clear?
Yes,
So
sir.
this is your engine. That's it. And every engine will have a sliding part. This sliding part we call piston, and the empty volume over which it slides is called the cylinder. Okay. So when you buy a car will come with a cylinder, number of cylinders. So if you see it's having 3-cylinder engine. So a low range car will have the 3-cylinder, like Nano will have, Nano I think will have only just 2-cylinder. Then slightly if you go above, it will have 3-cylinder. If you go for very expensive car, it will have the a large number of cylinder, maybe 4-cylinder. Then if you go for the Ferrari, Lamborghini, it will have 12-cylinder. So the question is why, I mean, how and why this cylinder will help you in creating a better engine. So cylinder basically means it is you can say a small system to perform the work. So more cylinder means you can perform more work at once. And so you can derive greater power. So as the number of cylinder will increase, definitely you're going to derive a better power. Of course, other things will matter. Okay, what is the overall body weight of the car? Because as you increase the mass and the size of the car, variety of things will change. You have to drive a higher mass, you need more power. So it is a constant endeavor to reduce the body weight of the car using some lightweight material like carbon fiber and so on. And in expensive car, they are using it as of now. Okay, but for the not so expensive car, they use a tin, they use some sort of alloy to give more rigidity but light. Okay, so you can also in plane what they use is duralumin, right?
Duralumin.
So which means it is an alloy of aluminum, because a plane has to fly, so it should be as lighter as possible, but it should not have the less in terms of rigidity. So because the entire weight of the plane is kind of held by the wings, or vice versa, the plane has to hold the wings together. So it should be light in weight, but it should be very, very rigid as possible. A pure aluminum is not so rigid, so we make an alloy of aluminum, which in turn makes it a very rigid object, which can sustain the weight. So the same goes with the design of automobile. Okay, so when you design any automobile, you need to create a lighter weight option, because you want to derive more mileage for the given power, and power is constrained by the number of cylinders. So if I have less number of cylinders, I cannot produce infinite power, so I have some restriction. Apart from the power, what comes is called the cycle. Okay, I mean the piston movement. So a piston will go from one place to another place, and while going, it will sweep volume. Okay, so generally piston can go almost up to zero volume, something like this. And there is a small gap which I have left intentionally, because we cannot compress the gas to zero, because we never create vacuum. Okay, so as you compress the gas, and although the exhaust will take out the gas, some gas will be always left out. Okay, and therefore you cannot keep on compressing forever. So there is something called the clearance volume. What we call clearance volume. So every piston will have clearance volume, and this volume swept by the car is called the volume of engine. So they always add all volume of every cylinder. Let's say if you have 3 cylinders, so let's say there is a car with Maruti 800, very famous car. So 800 cc is the volume swept by the cylinder in Maruti, and 800 cc, if it is 3-cylinder car, so divide 800 by 3, then each car is sweeping how much volume? How much? 267 or 33?
266.6.
So roughly, if it is 3-cylinder car, then every cylinder is able to sweep 266 ml, milliliter of volume. It's cc means cubic centimeter, which is like milliliter. Now 800 is the round figure. They always, when you read the specification, it is always a fraction, less than 800. It is 790 something. Okay. So that clearance volume will give you the actual sweeping volume, and the sound of the car actually depends on what volume you sweep. So if you have the bigger engine, the sound will have more, you can say it's a very coarse sound. Okay, and as the volume will shrink, the sound will be more, you can say, irritating, or you can say a high frequency sound will get, because in a bigger cylinder the volume shift will be not very fast. I mean, you will shift one volume, because that itself is very big, so the piston will move to and fro at less frequency. But in a small car, I mean a small cylinder car, the piston will sweep to and fro at high frequency. Okay, and as you increase the volume, the sweeping will be less in general, and therefore the sound quality will change. So from the sound itself, you can understand, okay, what is the volume of the car. So you can understand, the bigger the volume, the more the sound will be more, I mean, impactful. You can understand the sound. Okay. So the piston will move to and fro, and it will only compress the gas within. So let me remove this. And as I said, the entire purpose of, oh, I think this I'll leave, I'll do another one. Let me draw a separate one. So this is the piston part. And eventually we connect this piston with the crankshaft, which in turn will turn the wheel, and that wheel is connected with the chain system actually. And through the chain system, you drive, drive the actual wheel. So we have two wheels. Of course, one is the wheel because moving because of the engine part, but we also have the chain system, which in turn drives the connected wheel. So every bike will have a chain. In fact, every car will have a chain. Then again, the chain means it could be a belt drive, it could be a chain drive. So again, it depends on the quality. Okay. So in an expensive car, they use belt drive because belt drive are better at transmitting power. Chain drives will also dissipate power a lot. So in bikes, generally they have a chain drive. Okay. So it depends. How they design, because I am not into automobile industry, so I have less knowledge. And yeah. All right. So now the gas is confined. So when you study thermodynamic, what is your system? Is it cylinder, piston, or the gas?
Gas.
So this is your system, gas. And to derive the mechanical work, we need to confine in a closed volume. The gas should not leak out. Okay. And the piston is you can say the immediate surrounding of the system. If system is my gas, the piston is the recipient of power, isn't it? Because the rest of the wall cannot move. So when I do some work, who will receive my work?
The piston.
So my work will be received by the immediate system. Immediate surrounding. And for me, if I'm calling the me means the gas, for the gas, the immediate surrounding is the piston itself. Of course, the walls of the cylinder is also surrounding, but that is immovable surrounding. And therefore, I cannot perform any work on that part. Yeah, of course, some of the heat produced can be absorbed by the piston. But generally, we believe that, okay, if the walls are adiabatic, it will not take any heat. Or if it is metallic, it will take heat a very small amount to raise its temperature. Okay, so the gas is your system. The piston, which is movable piston, will be the immediate surrounding. So any amount of work which will perform will actually go to the piston, and piston is also in connection with the immediate surrounding to the piston is, if I think piston as a system, then who all are its surrounding? So in general, it is atmosphere and the gas. Generally, we never represent the atmosphere. So even the atmosphere is like a gas, isn't it?
Yes.
So now this is the two-step process. You give energy. You may give energy to your system. And once this will receive the energy, it will try to do some work. And once this will work, the piston will get this energy. So the work by the gas is the energy received by the piston. So work done by the gas is energy received by the piston, right? And again, with that energy, piston is free to do whatever it wants. So it may accelerate itself, it may increase its kinetic energy, it may compress the atmosphere. And when the piston will compress the surrounding air or the atmosphere, it is like the piston is not doing work against the atmosphere. And when piston will do the work against the atmosphere, the energy given to piston will go to whom? Will go to the atmosphere. Understood what I'm saying? Hello.
Yes.
Yes, sir.
So what is happening here? You see, you give energy to the gas, which is your system. And why you're giving energy? Because you want that the work should be derived. In fact, this entire arrangement is what we call heat engine. The job of the heat engine is to convert the energy, heat energy, into mechanical work. So we are just trying to achieve the reverse process, because we have been knowing this fact that, okay, heat can be produced using work. And now it's a reverse process. I'm trying to derive work by supplying the energy. Okay. And it is facilitated by the gas which is present. So once you give energy, the gas will try to expand, and as a result, it will do some work against the piston. The piston will receive some part of energy, which is equivalent of the work, and that energy it can again do in order to compress the atmosphere. Or if it is connected to something else, let's say if you connect a spring to the piston, then if you're compressing or elongating or compressing the spring, you're also giving energy to the spring, isn't it? So if you compress or elongate a spring by X, how much energy you supply to the spring?
Half kx.
Half kx square. So a spring is also a recipient of energy, but all this energy has come from where? Either the energy required to compress the atmosphere or the energy required to compress the spring has come from the work done by the what?
Gas.
Gas. So that is what you are supposed to remember. The work done by the gas is, of course, the work is like amount of energy transferred to the piston. So whenever gas will work, it will always transfer energy to the piston, and from there onwards, it can have, if it is having some sharing mechanism, it can share with other system as well, or it will keep with itself, or it can do whatever it wants. Okay. What you are concerned about, you should be only concerned about the piston, which is the moving part of this system. So generally gas is invisible. So the impact of work, I mean, I cannot see how much gas is working. What I can see is how much my piston is moving, right? So that is only visible thing. Can we see the gas? Yeah, of course, you can see here on the blackboard, but in general, you can't see the gas. So the work done with the gas is not visible. So we always look for the immediate surrounding. Which one? The movable immediate surrounding. And once we see the movable immediate surrounding, we know this guy is gaining energy because of the work done by this system which I have designed. So this piston cylinder arrangement, this piston, just a minute. Piston cylinder arrangement. Okay. So when you apply some, see, the gas will have some pressure P. So we assume that, let's say this is the equilibrium pressure. And as the piston will go away, the pressure may change. But for elementary displacement, can we take that pressure to be almost constant? Tell me
Yes.
guys, can we take this as almost constant?
Yes.
So if I assume the piston has only displaced by dx, what is the force on the piston by the gas? And not by others, like not by the atmosphere. Only what is the force by the gas? So force on piston by the gas is equals to P into area. Let's say A is the area of piston. A is the cross section area of piston. Okay. So what is the force on piston by the gas? Can what PDA? Tell me. Yes or no, guys? Tell me. And if this is the force, what is the work done by the gas? dW by the gas is how much? So work is defined as
PADX.
F dx, which is P dx. But what is A dx?
dV.
dV.
So in case of gas, we never write the displacement, we write the change in volume. So the F dx is replaced by P dV, where P is the instantaneous pressure, not the constant pressure. P is not always constant except the isobaric process. In every other process, the P have to be replaced in terms of V to make it integrable. So now the work done by the gas is how much? Integration of P dV.
Yes.
And how to get P? So to get P, draw FBD of piston. So in our syllabus, we have to study the thermodynamic processes which are quasi-static. Quasi-static means the changes are happening at elementary level. A small change will happen at once. And the benefit of quasi-static processes is that the system equilibrium can always be assumed, which means we are not going to consider piston to be accelerating at all. So what I'm trying to explain here, that for quasi-static process, I hope you remember the quasi-static process in the very beginning I explained.
Yes.
So for quasi-static process, piston will be non-accelerating. Therefore, the net force on piston, the vector sum of force on piston must be. So when you're solving any thermodynamic question, without any doubt, always assume the net force to be 0. In fact, in most of the cases, they will tell you that the piston is massless or piston is whatever. But for quasi-static process, you can always make the net force to be 0 to get the pressure. Okay. So PdV is very easy, but I'll show you some different orientation of piston in which you have to think slightly more than PdV. So imagine if I have a piston which is kept vertically. So what we have now, a vertical piston. And the mass of the piston is m now, and the gas is confined here. Atmospheric pressure I will call P naught. Area I will call A, and it is vertical cylinder. Can you draw the ABD of the piston? And tell me what is the pressure of the gas? P is how much?
P naught plus mg by E.
So P turns out to be P naught plus.
mg by E.
So if, let's say, if this will gas expands, if it goes up by X or Y, whatever, then in this case, the work done by the gas will be how much? It is PdV. And that's why it is P naught plus mg by A into dV. So now what the work done by the gas is how much? P naught plus mg by dv. And now you can write as P naught dv let's say you go by x, so you can clearly see. Let's say I say this as h. It looks nice. So this will become P naught is constant because the atmospheric pressure is not changing. So dv we can write as ah. Correct, guys? And here mg by a dv. Can we write this as
MGH.
yeah, it's exactly dh. You can call dv as a dh. That's why it's, and therefore this will become mg h. Now what you learn from here? You learn that the work done by the gas is actually going into compressing the atmosphere. See, I'm doing the work on the piston, but piston has to go against the gravity. In a way, you can think this way. Either you do this rigorous calculation or you can do mentally. What is the mental answer for this question? If the piston has gone up by h, the entire atmosphere is compressed by what volume, guys? Ah volume.
Yeah.
And when you compress the atmosphere, you have to work against the atmospheric pressure, right? You have to do the, I mean, do the work, you have to give the energy. So how much atmosphere will consume energy if you want to compress? Pressure into volume change, right? P naught ah. Am I right? Because the atmospheric pressure is constant and we know the volume change is ah, isn't it? Hello, hello.
Yes.
And
Yes.
because the piston has gone up by h, you have also increased the potential energy of piston by what value? mgh. So that to increase the potential energy of piston or to compress the atmosphere, we need some energy, and all of this energy will come from the gas itself. So either write the ABD, get the pressure and do the PdV, or you can do this by common sense. You know what is the compression of the atmosphere, always at P naught into the AH, and if there is a change of potential, you can add mgh. In fact, if I introduce some friction between the edges of piston and the cylinder, and if I assume the friction force is constant, I can also write the frictional loss of energy. So in that case, the work done will be not the two terms, but the third term will come, which is the frictional work, FH. Understood what I'm saying?
Yes.
And that FH is the loss part. So you have given, so you might have given some energy. Let's say, if I tell you that if I give energy Q to a piston, I mean to the system, and the piston goes up by H. Okay. And you're not supposed to know first law. Anyway, you can just solve the first law. If the piston has gone up by H because of the energy given, so out of the energy Q, how much energy is the gas consumed or delivered to his neighbor, the close friend piston? So you receive how much money from external source?
Say P naught AH plus MGH.
No, how much money you received? Money means energy. You
Q.
received Q energy, right?
Oh, the gas, yes, sir.
U means always the system. My system is gas. So how much energy gas received here?
Q.
Out of this energy, how much you gave to the best friend, your neighbor,
P naught
Mr.
H.
Piston? No, you gave P naught H plus MGH.
Plus MGH.
So how much energy is left?
Q minus P naught H minus MGH.
And if that energy is not consumed, so what that energy will do to you?
Work.
It will increase your internal energy, isn't it?
Yes.
Yes,
So
sir.
this is the conservation of energy. So you receive some energy, you do some work, because see, I am doing the work, so I am consuming part of energy, and the difference is actually So you receive something, you do some work, and the difference is changing the internal energy of system. So the way, of course, I never write this way. I mean, this is the way I always write is the amount of energy given will do two things. It will be consumed by the system in performing the work, because that is the purpose, right? And here work is done by the system. System is gas. Who is doing the work? My gas is doing the work. So definitely, if you are allowing the gas to do the work, it should have some energy to perform the work. So what is the definition of energy? What is the definition of energy?
So the capacity to do work.
Yeah, so it means your work, the amount of work is, already predetermined by the energy you have. So can we work more than what we have?
No, sir.
So we can either work equal to or less than, but we cannot work more than that. So out of this energy, I have done some work. If it is not equal, then I can also increase the internal energy of system, isn't it?
Yes.
So here you can write the delta U, the change of internal energy of the system is the energy given is Q. Always that in differential form, then you replace as you wish. So I know dq is Q and dw I got is after integration P naught AH minus mgh. And now if someone will ask me, find the change in temperature. So we know the relation NCV dt that I have derived already in the past. So the change of temperature is how much in this case? So no need to understand the first law. Think about the energy conservation, you will get all answer. So first law is not something new. It is actually conservation of energy itself. Okay. So delta T is how much? Q minus P naught H minus mgh upon NCV. And that is more than sufficient to get a very challenging question solved. So this is not an easy question. What you have solved is a challenging question. Okay. So PDV is of course work done. I'll just do this quickly. One more case. Sometime you will come across a spring-based problem, especially in advance. And there students get very panicked. Okay, when they say this question with spring connected, they simply get panicked. What to do now? But if you understand the process, you can solve most of the question mentally. So I'm going to attach a spring in its natural length, which means there is no deformation. Okay. So initially, the spring is in its natural length, but as you give energy, the temperature will change, the gas will try to expand, and as a result, piston will slide towards right, isn't it? And what I have told you that always assume the system to be at equilibrium, the mechanical equilibrium, right? Laws of motion will be net force equals to 0. So if the piston goes towards the right by x, and of course there is a atmosphere which I have not shown, and it will never be shown to you, rather it will be given to you. I assume the atmospheric pressure is P naught or PATM, whatever. Now, can you tell me how much work you have performed here? So in this expansion process, how much energy you consumed? Hello, tell me.
So
Sir, P naught AH plus half KX square.
Exactly.
Okay, sir.
So the work is very simple. The work done by the gas in this case is, so of course, P naught H AX plus, because you have elongated the spring, so you also need to supply the energy, isn't it?
Yes.
And out of the energy Q, this much you consume in the due process. So how much energy is left to change the internal energy?
Q minus W gas.
So is it very difficult to solve?
No.
And now you know how much temperature change will happen. Okay. So you're going to get question something like this. Spring will come. I see. In fact, if I give you any complex question, if you really differentiate the system and the surrounding, you can always understand what needs to be done here. Okay. If you think in terms of energy, you can solve any question of thermodynamics with the idea of work, energy, power. If you think as a first law of thermodynamics, it will be slightly difficult for you to solve. Okay. Now at equilibrium, what is the pressure of the gas at equilibrium? How to get the pressure of gas at equilibrium at final position? So pressure of gas at final position will be how much? Any guess, guys?
Kx plus P naught A.
Correct. So it is PA equals to Kx plus P naught A. And from where we are getting the answer? From the ABD of the piston, right? So spring will pull it Kx like this. The gas will press it PA. Atmosphere will push it P naught A. And now you know this answer. So P of the gas is how much? So if you would have integrated the answer PdV, the answer would have been same, which you got by common sense here. Understood?
Yes.
Yes.
Okay. Now after this, we have to do the graphical analysis. Graphical analysis. So graphically, if you draw the PV graph, pressure versus volume graph, so the area under the PV graph will give you what? So let's say there's a thermodynamic process which goes from V1 to V2. So if I draw a small part of it between, and let's say the pressure here is P, and this is V plus dV. What is the work done from here to here? What is this area? This area is how much?
PdV.
EDV.
So you can say dA is PdV, which means by definition this is dW. So the total work is how much? So area under the PV graph will give you what? Always work. But you have to be careful here, because here we have to also think about the sign convention. Why sign convention? So generally we have designed our system which can perform the work, and gas can naturally only expand, isn't it? Is it possible for gas to compress itself?
No.
So every gas is supposed to expand only. So when a gas is working, then it is understood that it is expanding. So an expansion work is said to be positive, and any compression process is said to be work is said to be negative. So here the arrow will matter. And if you look at the arrow, in the due process, the expansion is happening or compression? Tell me.
Which process?
This, the green line is the process.
Sir, expansion is happening.
So the work will be. So when you find the area, take it with positive sign. So expansion work always positive. Compression work because we have designed the system to do the work, and my system will only work when it will expand. So any expansion is work done in my system, and any compression is work done on my system by somebody else. So you can say that work done by the system is negative now. And negative work done means the system has absorbed energy. Understood? Hello, hello, hello.
Yes.
And
Yes.
negative work means instead of giving, the system itself is taking energy. So if you compress the piston from here to here, if it is reverse, then the energy of system will be Q plus P naught. How much? So how much energy it is receiving? P naught H, isn't it? The atmosphere will give the energy. You're also giving energy. Atmosphere is also giving you energy. Okay. What else? Any other energy?
Sir, the spring.
Now, should we take the spring energy? Yes, because so the work done by the atmosphere will be, the atmosphere will work to compress the spring as well, isn't it?
Yes, sir.
So now you will receive this energy, but that energy will be stored in the spring itself, right?
Oh, right. Yes,
Half
sir.
k square is the energy stored in spring. So is this energy going to gas actually?
No, sir.
So there is a rule. Actually, this is the energy, not this is the energy, this is the work done by the atmosphere. Out of this work, how much energy gas will receive? Out of P naught H, the half k square is going to the spring itself. The gas will receive the difference of energy. How many of you realize this?
Yes.
Yes, sir.
This
Yes,
energy will come to the gas. Okay. So, I mean, if you draw the FBT, you will get the same answer. But by common sense, you can understand the atmosphere is doing work on the piston, and the piston will give energy to gas and spring both. Understood? So, atmosphere having direct interaction with piston or gas of system. Tell me.
The piston.
Atmosphere is interacting with the piston itself, isn't it? So
Yes.
every work will go to piston first. The work done by the atmosphere will go to piston first. Now piston will decide what to do with that energy. And we can see that the piston will give some energy to gas, but it will also give some energy to the spring. And because I know the spring is compressed by X, so I know how much energy is gone to the spring. If you subtract, you will get the energy received by the gas. I'm not solving using first law, second law, whatever. Common sense. So most of the first law of question you can solve by common sense. What is happening? How energy is coming, how it is going, how it is distributing. If you can think with clarity, you can solve any question. Anyway, so you will get the same answer if you draw the. In case of doubt, always draw the FBT. P gas, PA. If you compress, the spring will push you back, isn't it? In case of compression, and atmosphere will push you like this. So if you write the equation, PA plus KX equals to P naught A. So what is P? You can see clearly it's KX by A. And now you realize that why the answer was what I wrote. So PdV will give you what? So here, of course, it's negative answer because it's a compression. So you will get, what we get? Minus P naught AX, isn't it? Because dx is backward, right? Hello, hello, hello.
yes,
Yes, sir.
Pressure is right,
Yes.
and you're moving left, so you're compressing it. So anyway, so we have tried minus PdV, the value. So you can see that the work done by the gas we have to take here is negative, and you can see this is the work done. And negative means you're receiving the energy. Okay, anyway, if this is the work done by the gas, then if you apply the formula Q equals to work plus delta U, and so it will go this side. And what we wrote in the very beginning, the same answer we're getting here, isn't it? So the compression will have the different answer, and you can always solve the question by two methods. One, by writing the ABD of piston and then integrating or differentiating. And second is, the second method is common sense. If you know how energy flows in nature, you can solve. And therefore, the work energy power chapter is very, very crucial for you to understand. Okay. So in graphical, we have a process. In a process, if something is expanding, it is positive, it is compressing, it is negative. So if I draw a graph like this, so tell me the work is positive or negative here?
Positive.
Here work is, tell me guys, positive or negative?
Positive, sir.
So this is one type of question you have to solve. And see, the PV graph must be there. Sometimes what students do is they find the area under the PT graph or TV graph, and they think, okay, it will also give the work. Okay. It must be PV graph only. Now also will come to something called cyclic process. So cyclic process means you go through variety of process, but you come back to the same initial condition or same thermodynamic state. So in cyclic process, we have to be careful in finding the work. So you may get a single cyclic process, you may get a multiple cycle process at once. So let's say we have a process like this, goes right, goes down, goes back to the same position, let's say. Now here, when we have cyclic process, you're not supposed to find the area below the graph like this, as you used to do. Rather, only find the area within the graph. So for any cyclic process, you're supposed to find the area only within the graph itself. And then you can decide plus and minus with ease. So now you may be wondering why only within the graph. You can find the area not within the graph. You can break this into three parts. Because we have three processes. So the first graph, the first process, the second process, the third process. The first process will give you how much area? The first process will give you the entire area, right? Second will give you how much area?
0.
And third will give you this area. I mean,
Trapezium.
yeah.
So
Now
what
tell
if
me,
it's
the
straight line?
first area is positive or negative. This is, and this is. So what is the total area? W1 minus W3. So if you subtract the 1 minus 3, what will get? You will get the area
Area
within
inside
the
the
graph.
triangle.
Exactly. That's why in cyclic process, we don't do this separately. We only find the area within the graph and we are done. And now the question is, how to understand whether the work is positive or negative? You can see clearly if you break it down into small pieces, you can see W1 is bigger, right? And W3 is smaller.
Smaller.
So the net
Yes.
work done is going to be positive, right? But to remember in the examination, if the cycle is clockwise cycle, so it means at high pressure we have expansion and at low pressure we have compression. Can you see that? High pressure. Okay, not able to see. This is high pressure expansion and low pressure compression, right?
Yes.
That's why the work is always positive, because high pressure is deciding the answer. So for you, if you want to just remember the answer, for clockwise cycle, work we have to take positive. So find the area and take positive value. But if we have the anti-clockwise cycle, the work becomes negative. That's it. So you find the area value wise and put a minus sign before you substitute in the formula. Is this clear, guys? I hope this is clear.
Yes, sir.
Now sometimes you'll get the multiple cycle, like not one cycle. So in the cyclic process, one question is very, very important that you will come across, and it is very standard. Like it's like the most prevalent problem. If the shape of the process is exactly like a circle, and if I put the arrow clockwise, so work will be positive, negative?
Positive.
Positive, sir.
Yeah, no need to think much. Just assume positive. But the question is how to find the area. So for
Inside the
size,
circle, sir.
yeah, but how to write the area? Let me give you some range. So given this is P1, this is P2. Given this is V1 and V2, how do I find the area of the circle?
Pi V2 minus V1 by 2 whole square.
So if you do so, it will be dimensionally incorrect, isn't it? So you cannot write pi r square, you have to write pi rx ry. A radius from the x-axis and a radius from the y-axis. So the way of writing is pi. From the x we can write as V2 minus V1 by 2. And from y we can write V2 minus. So that is why I said this is very standard problem. You must know this answer. I hope this is clear, guys. To keep dimension of the work intact, you have to take radius from both axes once, right?
Yes.
It is clear, guys. Tell me.
Yeah.
The third variety is when you come across, and this is very, very standard. I mean, this is very, very important. In fact, this question is already asked in the variety of mains question. What if you come across not one cycle, but cycles? So here's the cycle. So it is going this way. I mean, this way. So it is making 8. Okay. You make it look reti 8. We can do like this. Okay. So what will the answer here? Can you guess?
Total area.
So okay, tell me the work is positive, negative first of all.
Negative, sir.
Very good. So in case of multiple cycle, we look for the bigger cycle first. Okay. So bigger will decide the answer. So in a big cycle, you can see it is anti-clockwise and small is clockwise. So if I assume this area is A1, this area is A2 value wise, my work will be minus A1 plus A2. Is this clear, guys?
Yes.
So you will come across question like this from work calculation. Okay.
Sir,
Yeah, tell me.
sir, in the previous question, the V2 minus V1 by 2 and P2 minus P1 by 2, those values will be the same, sir.
I didn't get your question. What are you saying?
Sir, we are
In this
finding
case,
like in the
okay,
previous ones, the
in the
single
previous
cell.
one, yeah, this is fine.
Sir, here like both those values will be the same, sir.
No, no, they will give you values like P1. Just a minute. So now we have too many values, right? P1, P2, P3. Okay. And then, so they will give you sufficient values, which you can always use to determine the X radius and Y radius. You know, if you know V1, V2, you can find the V1 dash and V2 dash. Do you know this? In the ratio of radius, right? Because the pressure difference and the radius will have some proportional relation, isn't it?
Yes.
Yes, sir.
So by taking the P relation, you can find the V relation. Like a P2 minus P1 by V2 minus V1 will be same as what? The ratio will be same as P3 minus P2 upon. So they will not give you all answer. You can find this relation. So V2 P3 minus P2 upon P2 minus P1 and V2. So sometimes you have to use this relation. And then you have to find the area of each graph separately by the same method, this method. Yeah, formula remains same. If it is circle, it is same. Okay. So the formula remains same. It is pi into Rx Ry. Is this clear?
Yes, sir.
All right. So I have to stop the lecture here only.
So,
And yes.
so what if it's a straight line?